In this video, we will use Newton's second law to solve the following problem, which is connected to our previous video. Traveling at the speed from the previous problem, 17.0 meters per second initially, the snowboarder slides across level ground before coming to a stop. The snow here is a bit slushier, with a coefficient of kinetic friction between the board and the snow of 0.222. And we are asked, how far does she travel as she comes to a stop? Well, the first step in the problem-solving process is always to draw a diagram showing the information that you're given and the forces acting on the object. Now, in this case, our snowboarder is traveling along level ground, and she has an initial velocity of 17.0 meters per second. Saying that she comes to a stop means that she has a final velocity of 0. She travels a distance, delta x, which is what we are trying to find. Now, immediately we might think that we would be using this kinematics equation, as we have done in the past, to find that value of delta x. The problem being, we do not know the acceleration. Now, that acceleration is going to be in this direction, opposing the initial velocity and bringing the snowboarder to a stop. So we can use Newton's second law to find that acceleration. We'll complete this step by drawing the forces that are acting on the snowboarder. And those forces are the weight force, straight down, the normal force, which is always perpendicular to the surface, and in this case that means straight up. Because the surface is horizontal, the normal force is going to be vertical. And then finally, we put in the friction force. Note that since the snowboarder is traveling to the right, that means our friction force is going to be to the left, because the friction force always opposes motion. And we can also make note that the coefficient of kinetic friction is 0.222. So we've drawn a diagram containing all the information we were given and showing the forces acting on an object. The next step is to develop a coordinate system for the problem, and in this case the coordinate system is very straightforward. We can adopt a traditional x and y coordinate system, with x being to the right and y being upward. It is usually a good idea to have the positive direction be the direction that the object is moving. So since the snowboarder is moving to the right, we will have positive x be to the right. So a traditional horizontal and vertical coordinate system here is good for our use. Having established that coordinate system, the next step is to ask ourselves, do any forces need to be divided up into components? If so, draw those components and come up with formulas. Well, we can skip this step in this case because the forces are either purely vertical or purely horizontal. In our coordinate system, that means that two of them are purely in the y direction and one is purely in the x direction. So there's no need to divide up into components. And then we say, all right, let's use Newton's second law to figure out what we need to figure out. Now, in this case, we're going to be looking for the acceleration in the x direction. That is what is going to go in our equation here. Since the snowboarder is not moving up or down, we can say that the acceleration in the y direction is going to be 0. She's not moving up or down. There is no acceleration in the vertical direction, in the y direction, and so we can say the acceleration in the y direction is 0. Right, so now we write out Newton's second law. Remember that because of the vector nature of force and acceleration, we can actually write two equations for Newton's second law, one for the forces in the x direction and one for the forces in the y direction. Now that acceleration in the y direction is going to be 0, and so the sum of the forces in the y direction is going to be 0. And there is our target right there, the acceleration of the snowboarder. So let's focus on this equation first. There's only one force in the x direction, and when there's only one force, it is really easy to add up the forces. So all we have in the x direction is the friction force, and notice that force is going to be negative because it is to the left, and we say that to the right is positive. We put that negative sign in there to show that we know that the friction force is opposite to the direction that we have called positive. And that's all. That's all we have to add up. And we look at the formula for the friction force, and it is mu k times the normal force. So now, as happens so many times, we have to figure out what the normal force is before we can figure out what the friction force is. For that, we turn back to our diagram and we see we have two forces. In the y direction, we have the normal force positive up, we have the weight force negative down, and those two forces are in equilibrium. The only way this can be true is if the normal force equals the weight force. Remember, you should never assume that the normal force equals the weight force. Never assume this. Always work it out. It's very easy. We've seen in previous examples how sometimes the normal force is not equal to the weight force. So do not ever assume this. Always work it out and figure out what the normal force is. But in this case, on the flat surface, the normal force does indeed equal the weight force. And so we take this and plug it in here. And so our formula for the friction force becomes negative mu k mg. Note the masses cancel. Mass is not relevant to this problem. And we wind up with the result of ax equals minus mu k times g. And that works out to be negative 2.18 meters per second squared. Note the negative sign indicating that the direction of the acceleration is opposite to the direction of motion. Right, well now we can turn to our kinematics equation here to finish out our task. So here is kinematics equation number 3. And we know now what most of the things are here. The final velocity is 0. The initial velocity is 17 meters per second. The acceleration is negative 2.18. That negative sign is absolutely essential. Absolutely essential. And so 17 squared is 289. 2 times 2.18 is 4.36. We take this factor over here and it becomes positive. And so we arrive at the conclusion that delta x equals 66.3 meters. So we bring this factor over here, it becomes positive, and we solve for delta x. That gives us a delta x of 66.3 meters. So the snowboarder travels a distance of 66.3 meters before coming to a stop.